Hello, everyone. I welcome you all to our social learning session. And our first speaker is Ron Peretz, who will present a paper on granular DeGroot dynamics. Ron, the floor is yours.
Okay. So first of all, I would like to take this opportunity to advertise a workshop that we plan in February 23. It's going to be in Bar Ilan, which is very close to Tel Aviv, in Israel. So if you might be interested, you can check it out on the internet and send us an email if you're interested. Okay, so now for the talk. So the title was very long. It was it's about robust, naive learning in social networks. So let's.
Hey, sorry to interrupt.
Yeah.
The virtual room does not see any slides.
Okay, fantastic. So for those who missed it, it's the most important part of my talk. This is the workshop. And now I will try to break down the title into small pieces. So it's about robust, naive learning in social networks. So let's first with social network. So in this presentation, a social network is a connected graph, undirected connected graph. And the agents are the vertices in this network, and they have opinions. Their opinions are real numbers. The initial opinions, so what you see here is the initial opinion of agent I at time 0. And it's composed of mu, which is going to be the true state of the world, plus IID noise. So and then we assume that the noise is bounded and has mean 0. Okay? So this is about the initial opinions. Now what is the dynamics? So this is, actually I was told it should be pronounced DeGroot. I presented this in the Netherlands, and I learned that it should be pronounced DeGroot, so I'll try to stick to it. So what is the DeGroot dynamics? The timing is, the time is discrete, and all the agents update their opinions simultaneously. And when they update their opinion, what they do, they just look at their neighbors in the graph, and they compute the average of their neighbor's opinion, and they update their own opinion to be the average of the opinions of the neighbors. So that's the DeGroot dynamics. Now, some classic results. So this is DeGroot himself from 1974. He assumed that the graph is finite, and then he showed that the limit of at any other time, so in the odd times and the even times, there exists a limit. And if the graph happens to be non-bipartite, then there is consensus. What does it mean? It means that the opinions converge. If you take the time even and odd times, the opinions converge, and the limit has a very nice expression. It is just a weighted average of the initial opinions, and the weights are those pi i's. These are the weights of the stationary distribution of a simple random walk on the graph. So these are classic things. Now, Golub and Jackson in 2010, they had the following observation. If the initial opinions are IID and the maximum of the pi i's is small, then the limit in the odd times and in the even times is close to mu with high probability. Okay? And they called it naive learning. Why is it naive learning? It's naive because the rule is very naive. You don't do any strategic things. You just take the average of the opinions of your neighbors. And it's learning because it gets close to the true state of the world, which is the thing that they want to learn. Okay, this is why it is called naive learning. Okay, so now let's start with theorems. So the first theorem is just a warm-up. It's an exercise. So let's consider the DeGroot dynamics on an infinite graph. infinite connected graph, and the degree of all the vertices is bounded, then in general, even if you take the even time periods, the limit need not exist. It might diverge. But if the initial opinions are IID, then the limit exists, and it's exactly the true state of the world, almost surely. Okay, this is an exercise, but we're going to use, well, this theorem is useful for the rest of the result that we have. So let's continue. So now we want, so these are very nice things about the Chorot dynamics. It does this naive learning. Now let's see what are the not so nice things. And the not so nice thing is what happens when you have some agents who do not play by the rules. Okay? So we will consider two types of such agents. One is called a bot, or a stubborn agent, or a lobbyist. There are many names in the literature. This is an agent who starts with a certain initial opinion and never updates its opinion. So this is a bot. The other kind of agent who doesn't play by the rule, these are agents who have distorted monitoring. So these agents, they observe the opinions of their neighbors, but they seem slightly differently than what they really are. So for example, you may have an agent that looks at the opinion of its neighbors, and he's optimistic. He adds 1% to this, or maybe subtracts 1% to the opinion. So they see a small distortion, but the distortion can go in any way. And what the problem with the Chorot dynamic is that it is fragile. So even a single bot or a single agent with slightly distorted monitoring can dictate the outcome, the consensus. Okay, if you have one bot and the graph is finite, then in the end, everyone will adopt the opinion of the bot. And if you have someone who is slightly pessimistic, everyone will go down to 0 at the end. Okay, so these are problems. As you can see here, it's a sad thing. So here's the solution. The solution is the granular DeGroot dynamics. So this is the 1/m DeGroot dynamics. So it's similar to the DeGroot dynamics, but the opinions are always rounded to the nearest integer multiple of 1/m. So you have a certain grid with distances 1/m, and you always following thing. First, you observe the opinions of the others, and you round them to the nearest point on the grid. And then you compute the average, and the average need not be on the grid, so you round it again to the nearest point on the grid. Okay, there is one delicate thing about this rounding, and it's important. If there is a tie, when you want to write, you compute the average, and then it happens to be right in the middle between the opinions of between the 2 points on the grid, then you use your own opinion as a tiebreaker. So you take you decide towards the point on the grid which is closer to your current opinion. So and it's important. Without it, it doesn't work. Okay, so here's the simulation. I want to show you through a simulation that this modification really does the job. So what you see here in this picture, I will tell you. So the graph is 100 by 100 grid. Okay, this is the graph. And the opinions are numbers between 0 and 1. The initial opinions have the uniform distribution. So what you see on the left, from your side, well, my right-hand side, okay? What you see is the initial opinions. Okay, so you see it's random. And then you see what happens after, I think, 10,000 rounds. This is the middle picture. So the upper one is the Granular DeGroot, and the lower one is the Standard DeGroot. And the size of the M is 100. And there is one bot. You can spot this bot. His initial opinion is 0. So as you can see, the bot has a certain radius of influence, both in the Dechorot dynamics and in the 1 over m Dechorot dynamics. And then on the other side, my left-hand side, it's 1,000, 100,000 periods. Then in the standard Dechorot dynamics, the opinion of the bot covers the entire graph. And in the 1 over m, the granular Dechorot dynamics, the agents manage to learn the true state of the world, except for a small radius around this bot. So we actually succeeded in our mission. Okay, now this is a simulation, and we have some rigorous theorems. So this is our first important theorem, theorem 2. The 1 over m Dechorot dynamics converges in any other time period on any graph of sub-exponential growth rate for any bounded initial opinions. So if the initial opinions are just bounded, don't have to be IID, and the graph has sub-exponential growth rate, then, or on finite graphs it works as well, but also on infinite graphs with sub-exponential growth rate, then the opinions do converge. And furthermore, the same holds in the presence of bots. So even if there are bots, we still have convergence, and also distorted monitoring if the monitoring is smaller than 1 over 2m. This is just because this rounding eliminates the distortion. So this is not a big deal. And the second theorem says that the 1 over m Dechorot dynamics achieves approximate learning, namely that this limit that we know that exists is with high probability it's going to be close to mu when t is large enough. So the limit is going to be close to mu with high probability under some assumptions. Okay, and we have a very long list of assumptions and conditions. Maybe in the future we can relax some of them. So the first one is that the initial opinions are bounded IID with the correct expectation, with expectation mu. The second assumption is that the graph has not just sub-exponential growth rate, but stretched sub-exponential growth rate, meaning that the growth rate is smaller than an exponent of x to the power alpha for any positive alpha. So for example, polynomial growth rate is okay. Okay? And another requirement is that the degree of the graph is bounded. And finally, it only works, okay, bots and distorted monitoring are allowed as before, but this convergence, this good learning happens only for agents who are far enough from the bots. As we saw in this simulation, those who are close to the bot get impacted by the bot, but those who are far enough from the bot, they are not impacted, and the distance that you have to be. So we managed to find something, some radius, and the radius is polynomial in all the parameters, but maybe it can be improved. We don't know. We don't think it's what we found is optimal. This is why I didn't mention the radius here. Okay, so I'll try to say one more thing about the result. So the result is more general than just the granular DeGroot dynamics. It applies to any dynamics that satisfies three properties. And the three properties are called monotonicity, approximate averaging, and robustness. And I will try to explain what robustness means. And this is, once you have robustness, you have convergence. This is theorem 2. And once you have the three properties together, you get convergence to the correct value. This is theorem 3. So I'll try to show you what robustness means. So this is the definition of robustness. Gamma eta robustness has, it has a definition. I don't have time to really explain why this definition works, but this is the definition. You can stare at it a few seconds. Okay? So it looks very weird. It means that it bounds the amount by which the opinion at time t+1, the difference between, or the change in opinion between the opinion at time t+1 and t-1 is bounded by some quadratic function. But we found other dynamics that satisfy these properties. So our theorem is more general than just the one over the DeGroot dynamics. And now, as you can see now, I will show you that there exists a proof. Okay, we'll go very quickly through it. You see, there is a proof. And I think with that, I will finish. This is a thank you.
Thank you, Ron. We have time for a couple of questions. Yep.
Yeah.
How do your results depend on M, like the degree of granularity?
What?
How do your results depend on the value of M?
The size of the graph?
M, like the 1 over M map, or...
Oh, the M. Okay. That's a very good question.
Could you take the mic?
Yeah.
And also repeat the question so that the online audience.
Okay. So the question was how our result depend on M. Okay. So there is a trade-off between taking a large M and a small m. So if you take a small m, what you get is you get that the bot has a small radius of influence. So this is good. But the quality of the approximation, so the limit is going to be very roughly approximate the true value. And if you take a large m, then the quality of the approximation becomes better and better. You get to learn very, very close to the true state of the world, but the radius of influence of the bot is going to be larger. So there's a trade-off between taking large m and small m. Yeah?
From the simulation you showed, like one intuition I got from like why granularity is helpful is somehow you sort of stop early something. In the other one, the bot keeps influencing for many periods, and then ultimately that drives everyone to the wrong thing. So like I don't know if this fits into if this like a
Yeah. So.
that fits into it. So maybe one dynamic you can consider is like whenever I would change my opinion by less than some epsilon parameter, I instead stay constant. So like I truncate away any change of opinion that's less than some small number.
Okay, so Kevin had a very good remark. He said that from the simulation, you see that what happens with the 1 over, if maybe I misinterpreted your intuition, but what I understood is that if you look at the granular DeGroot dynamics, it works like the DeGroot dynamics, but at some point it halts. Well, this is exactly what happens. And this is how what the proof looks like. We know that with the 1 over m, the Roth dynamics, there is convergence, and convergence means that everything is fixed from some time on because you only take values on a discrete grid. So, and once things are stuck, then nothing happens, nothing changes. So the bot cannot influence anyone anymore. So that's a correct intuition.